Hi, everybody. Yeah, I'm Zarija Lukic. I'm at Berkeley Lab, and I've been doing cosmological simulations, right? So you heard about numerical relativity. These type of simulations that I'll be presenting are done in Newtonian limit, right? So we don't use general relativity. We are steering away from compact objects, from details of that kind of thing, and we are modeling the universe as a whole. So let me tell you something about what we are doing. Like first, so why are we running these simulations? There are two main reasons why we need these type of simulations. One is to infer the cosmological model, to basically say something about the universe we live in, right? So the simulations provide the theoretical backdrop against which we can compare the actual observations, right? So once the models are too complex, the nonlinear evolution cannot be followed by pencil and pen, right? So now, if you want to determine for our particular universe, how much matter there is, what kind of matter there is, how fast it expands, and so on, you need to run numerical forward models to then compare observations against it, right? So that is the one reason, and the other reason is because cosmology is inherently observational science, right? So you cannot run experiments on a tabletop, right? So you cannot make a control type of experiments, but you have one universe and that's it, right? So then basically the simulations are needed to provide more mock universes, which are used to confirm the quality of analysis pipelines, right? Because even though your simulation may not represent fully the actual universe in all the gory detail, you can test, how certain analysis, when you propagate it through the actual data, do you get what you expect to get, right? Because basically in simulations, you know all the answers, right? So then you can use it for forecasting and for planning future cosmological surveys. And in existing surveys, it is used to help estimate the errors of certain observations, right? Because again, you can produce many simulated models, right? So there, for that reason, cosmological simulations are needed for many of the ongoing and future surveys. And there is a need to make a lot of these simulations, and there is a need to make them large in terms of volume and accurate and so on. So something like 2011, we started this effort on a Nix code. So it is our cosmological code, based on Eulerian hydrodynamics for gas. I'll say a little bit more in a moment, and body particles for modeling the dark matter. And it is based on AMRX, right? So back in days it was Boxlib, right? I mean, it's worth saying at this point, since this is an AMRX community meeting, that basically, so when we started Nix, before Nix, there were no particles in then Boxlib, now AMRX, right? So basically, so the whole particle component was originally developed for this specific application, and now it is used in many other applications. And if you ask me, that is kind of like a big strength of AMRX team, because they are not building a certain product and now, okay, here is the product and you can use it, and maybe it works for you, maybe it doesn't work for you, but they work more in a collaborative mode, right? So they have always invested interest that your application actually becomes a success, not only that it uses something, in this case, this specific library, right? So then basically it is possible to develop quite non-trivial extensions, like in this case, like it was the whole concept of now particles, for modeling matter. All right, so we are modeling the universe as lambda CDM, right? So there are three components. There is this cosmological constant mentioned in a previous talk, but that is the background thing, right? So basically that does not have any dynamical component. That just affects how the matrix evolves, right? But two dynamical components are the dark matter and the ordinary matter, or baryons, right? So dark matter interacts only gravitationally. It does not have pressure forces, so it is a collisionless fluid, right? Described by a set of Boltzmann and Poisson equation, right? So this thing is not easy to solve on a grid because being collisionless, what will be happen is that you will be having a multi-streaming, right? So basically, at the same point in space, you can have dark matter going in different directions, right? So you can have basically, because there's no collisions, right? So it kind of like transparently, it goes almost through each other, right? So basically, so that's why if you want to do it on a grid, actually, you would need a 6-dimensional grid, right? Because you need to represent both at every point in space. You need to represent also 3 components of velocity, right? And that's why basically, so this equation, so it has, it's actually 7, I mean, there is time, and then there is free space and free momentum components, right? So basically, so to make this problem tractable, we are solving solution for dark matter as an n-body problem. So the reason that we can do it is because it's a little bit of lucky thing also, is that basically all observations point to the dark matter being cold, which means that initial, so to say, velocity dispersion is pretty much non-existent. So that means that at least initially you can sample things in 3-dimensional space. And now once you start evolving them as an n-body problem, then basically with, particles being tracers, then multi-streaming is not going to be an issue, right? So basically, so you can have, multiple particles at the same point in space, right? And then the other component is ordinary matter. This is which is related to things which we observe, which it's going to be related to our observables. And that is modeled as an ideal fluid, like using Euler equations, conservation of mass, momentum, and energy, and then the closure is given by the equation of state, right? So basically, so these are the 2 components, and now basically in Xcode, right? So it uses this AMR-X framework to solve this gas dynamic problem, as you would do it in any CFD type of situation. And there are these dark matter particles, which are actually very strongly driving this gas through the gravitational force, right? Because most of the matter in the universe is in the form of dark matter. That's why it is kind of like the driving force, right? And oh, okay, yeah. And now here is a movie just to see how it looks like, right? So let me go back, stop it here, right? So basically, these are kind of like initial conditions. Like, so we started at a very early universe. The fluctuations are very small, right? So universe is almost homogeneous, but there are some fluctuations which will then gravitationally increase, right? Don't worry about that. But basically, okay. So we started with something like that, and then as the system evolved, now you can clearly see basically this whole structure of filaments, voids in between, whole bunch of dense objects, so that may correspond to galaxies and so on, right? So basically, so here we are looking at the evolution of ordinary gas in this particular visualization, right? And now basically, so what I was telling you originally is that basically if you change the cosmological model, then basically the structure of this will change, right? So basically, so maybe if for things, for some type of changes in cosmological parameters that we're interested today, you may not be able to see by eye, how this thing is different, but some statistical properties like 2-point correlation function and things like that will change. And then basically you can use that to say something about the universe, right? So because of this evolution, right? Because we started kind of like homogeneous situation, like relatively easy going, and then it goes into very clustered situation. The performance is in terms of how much time is spent in which physics component changes basically as the simulation evolve, right? So this is not a feature of, say, bad programming or poor parallelism. That is the feature of the problem, that basically as you get into more complex structure, then subgrid physics starts to dominate, right? So things which are happening, solving for different species, heating and cooling, things like that, they dominate, whereas in early stages, they are subdominant component, for example, and most of the time is being spent in doing hydrodynamics. All right. So exascale project was, we did not start with exascale project, we started before it, but exascale project was very important in getting us to scalability and to use basically modern architectures, right? So throughout the ECP, we managed to get, and this was mostly driven by Jean Sexton sitting there. She did this like huge effort of moving almost whole code base, which was CPU based onto GPUs, right? And of course, it leveraged the whole AMRX, right? So as the whole AMRX was moving there, then it was easier to port NICs as well, right? And here you see some scaling, right? So I'm showing weak scalings as you change number of MPI ranks or number of GPUs. So when we run on GPU systems, we tend to run with 1 MPI rank per GPU. So that's usually the model, right? And basically, so this is weak scaling. So that means we are increasing number of GPUs and we are increasing proportionally the size of the problem, right? So keeping under ideal situation, keeping the work per processing unit constant, right? And we would like to see then, in ideal case, we would like to see these lines being flat, right? And you can see that they are kind of flattish, right? So first, you can see that going from CPU to GPU, right, that we get quite a significant speed up, right? So that is immense increase in just capability, right? And basically going from red to blue line, this specifically, so this is not just improvement of GPUs, but this is like going from, early implementation of GPU code to actually more mature and so on. But basically going from CPU to GPUs, you can see basically almost like a factor of 100, right, in just premium performance. And then you can see that these lines are flat, right? So for us, that's important, right? So we care more about weak scaling than strong scaling, because we are not interested as much in going into deep details of certain places, right? But we want to simulate more of cosmological volume, right? So we want bigger simulations to get more of statistics and more representative sample of the universe. And let's see, do we have, so that's Perlmutter Summit. I think we have a Frontier and Aurora on this plot. Yeah, it's not a, yeah. Anyhow, so over the years, we've done, I think, yeah, I did not count, but I mean, there is probably something like 100 papers that use NICS results by now. I mean, not all written by us, and of course, but here is a sample of some works which kind of took more attention than some other works. Like we were able to use NICS simulations against observations to detect voids, to constrain reionization history, quasar lifetimes. Many interesting results, appearing in top journals, including Science. And it is currently, basically NICS code is used to produce simulations used with this big DESI survey. So this is one cosmological survey led by Berkeley lab. And basically NICS is producing hydrodynamical simulations which are used to constrain the cosmology, right? here you see basically how we were sampling, kind of like, for the Quasar lifetime paper, how we were able to use data and basically sampling different Quasar models to figure out kind of like the likelihood of certain Quasar lifetimes. Our latest work, again, we want to go for bigger volume, and this DESI survey brings really very important motivation for going into really, really big volumes, right? Because this will be the first time that we will observe density of quasars, density of certain objects on a sky. It will be dense enough such that you can such that in observations you can reconstruct some three-dimensional statistics rather than only looking at one-dimensional statistics along the line of sight, right? But basically on simulation side, that requires really, really large volumes. Like this is the example of a volume that kind of like ballpark represents the state of the art if you want to run, this particular type of cosmological probe, Lyman alpha forest, whatever, if you want to run it at a high accuracy, right? So basically, using OLCF frontier and using NICS, which can go to, use significant fraction of the frontier, in practical terms, we were able to get volumes up to this one, which you're seeing, right? So going from this guy to that guy, right? I mean, right? At different resolutions, right? So we cannot run this type of big volume and maintain super fine resolution that we would like to have here. But basically, we are able to go bigger than this volume, and then with different resolutions, we are able to produce, just at the end of last year, we were able to produce a new suite of simulations which are literally redefining the state of the art in the field, right? And now, kind of like as a step further, right? So we are trying to combine these simulations with certain AI models, right? Where we are producing low resolution X simulation, right? So we are training on a pairs of low resolution and high resolution simulation, right? And then, so once we train certain model, right? So we give it a new simulation. In this case, this was like in inference mode, right? So this specific simulation was not part of the training set, right? But basically we pass it through our network, right? Now the network doesn't know what the answer is, but we know we can run a higher resolution simulation and know the answer, right? And then basically we had a paper showing that that's actually possible to do, right? Is that enables us really to get to really big volumes and get the accuracy that we need to constrain cosmological parameters. And yeah, that's the end of my talk. Yeah, so kudos to AMRX team for making a lot of good things, and we are over the last 14 years we've been very happy users of their framework, and I mean, and again, not only their framework, but basically their intellectual capacity, kind of like they were really helping us a lot. Yeah, thanks.
Noticed that I think it's the very first slide. That's the artwork that's on the side of Froment. So
yes. I should. Yeah. So she's referring to this one. Yeah. So this is plastered on Promoter supercomputer. Yeah.
All right. Ben, you want to be standing up for your talk, and maybe time one more question for Larry.
I have one question, which is when you do this, simulations that you're showing, like the baryon density ones, like do you end up refining kind of pretty much the whole grid? It looks like so many areas have like high density or whatever whatever the visualization represents.
Right. No, that's a great question. Yeah. So in that simulation, so we use uniform grid, right? So for certain cases, like if you go to clusters of galaxies, then it makes sense to use AMR, right? Because you know where your focus are in simulations, and you are not resolving anything. But for example, when we go for Lyman alpha forest, a lot of signal comes from void regions, and then basically it's not efficient.
Yeah.
I mean, good question. Yeah.